In this video, I'll explain the proof of Lagrange's mean value theorem. See the statement of Lagrange's mean value theorem. Let f be a real valued function defined on the closed interval a comma b such that f is continuous on closed interval a comma b, and the second condition is f is differentiable on open interval a comma b. If these two conditions are satisfied by f, then there exists a point C in open interval a comma b such that f dash of C equal to f of b minus f of a divided by b minus a. Geometrically, f dash of C means slope of the tangent at the point C. It says that slope of the tangent equal to slope of the secant passing through the points a comma f of a and b comma f of b. That is shown here. You have an arbitrary function y equal to f of x. End points are a and b. Then draw tangent passing through a comma f of a and b comma f of b. Then you can always find a point C at which the tangent is parallel to the secant line. There may be more than one point at which the tangent is parallel to the secant line. See, this is an example. Here, this is the secant passing through the endpoints a comma f of a and b comma f of b. Now, there exist two points C1 and C2 at which tangents are parallel to the secant line. This is the geometrical meaning of Lagrange's mean value theorem. Now let us see how to prove Lagrange's mean value theorem. For that, I will define a new function phi of x as f of x plus k into x, where k is constant. Now I will prove that phi is continuous and phi is differentiable and phi of a equal to phi of b, so that I can apply Rolle's theorem on this function phi. The statement of Rolle's theorem is if any function is continuous and on closed interval a comma b, differentiable on open interval a comma b, and f of a equal to f of b, then there exists at one point C in the open interval a comma b such that f dash of C equal to 0. That is the statement of Rolle's theorem. So first let us make sure that the conditions of Rolle's theorem will satisfy for this function phi. See here, this phi is continuous on the closed interval a comma b. That is because f of x is continuous given in the statement of Lagrange's theorem. F of x is continuous on the closed interval a comma b, and this phi being the sum of two continuous functions, therefore phi is also continuous. See, phi is continuous on closed interval a comma b. Next, second condition is phi is clearly differentiable on open interval a comma b, because f is differentiable on open interval a comma b. K into x, it is differentiable. You can get the derivative of k into x on the open interval a comma b. Therefore, phi being the sum of two differentiable functions, it is also differentiable. Now the third condition of Lagrange's theorem is the value of the function at end points must be equal. This function is defined on closed interval a comma b. So the end points of closed interval a comma b are a and b. The third condition is phi of a equal to phi of b. This happens only if and only if you have to substitute x equal to a here and x equal to b. So we will get f of a plus ka equal to f of b plus kb. We have to find the value of the constant k that will make this happen, so that I can go with the application of Rolle's theorem. So therefore simplify this. Ka minus kb equal to f of b minus f of a. This implies take k common, a minus b equal to f of b minus f of a. So k equal to f of b minus f of a divided by a minus b. So for this value of k, phi of a equal to phi of b. So therefore, by Rolle's theorem, you can apply Rolle's theorem for the function phi now. By Rolle's theorem, all the three conditions of Rolle's theorem satisfy. The third condition satisfies for this choice of k. By Rolle's theorem, there exists a point, so I can write there exists a point C in open interval a comma b such that phi dash of c equal to 0. So phi dash of c is given by differentiating this function. So let us first find out phi dash of x. So phi dash of x equal to f dash of x plus derivative of x is 1. So it is k. I want phi dash of c. So phi dash of c is f dash of c plus k equal to 0. So f dash of c equal to minus k. So f dash of c equal to minus of, substitute the value of k, f of b minus f of a divided by a minus b. To avoid this minus sign, you take minus from the denominator. So you will get f of b minus f of a divided by b minus a, which is equal to f dash of c. Hence, we have proved the Lagrange's mean value theorem. There exists at least one point C in the open interval a comma b for which slope of the tangent equal to the slope of the secant line passing through the points a comma f of a and b comma f of b. Now here is an example. Verify mean value theorem for this function f of x equal to x square on the closed interval 0, 2. So first you have to check whether the conditions of mean value theorem are satisfied for this function f of x equal to x square on the closed interval 0, 2. It's a polynomial function, it's a parabola here. So clearly your f of x is continuous on closed interval 0, 2, and this function is differentiable on open interval 0, 2. Directly write the derivative of this function, that is f dash of x is equal to 2x. Keep this in mind. Therefore, now you can apply the mean value theorem for this function. Therefore, by mean value theorem, there exists some c belongs to open interval 0, 2 such that f dash of c is equal to f of b means 2 minus f of 0 divided by 2 minus 0. You have to simplify this now. F dash of c is, f dash of x is 2x, f dash of c is 2c, which is equal to f of 2, substitute 2 x equal to 2 in this function. So 2 square is 4 minus f of 0, put x equal to 0, 0 square is 0 divided by 2. So 2c equal to 4 by 2 is 2, c equal to 1. Now check, is this point within this open interval 0, 2? Yes, this clearly anyway we have chosen here belongs to the open interval 0, 2. Therefore, this is the point to which the tangent is parallel to the secant line. See, the graphically it is a parabola, y equal to x square is a parabola. Now on the open interval 0, 2 it is 1 and here it is 2. End point 0 and 2, passing through these endpoints we have this secant line. The point is 1. At this point the tangent is parallel to the secant line. This is how we got the point c equal to 1 within the open interval 0, 2. I hope you understood the concept. Thank you for watching.